the Agilent 33622A arbitrary waveform generator, we're going to perform the classic what value is a capacitor, what value is an inductor. If you look at the components that are laid out on the board here, you'll see that I have a number of random things that I pulled out of my junk box from previous experiments. I have 3 resistors here, a 1K, a 10K, and a 100K. I have a rather large inductor, which I have no idea what value it is. I was winding this for an experiment and never really did take the time to figure out what its inductance was, so we'll see if we can figure that out. And I have a range of capacitors. 2 of them, I can read them off right now and tell you what values they are, but I won't. But they're the 2 electrolytics. The smaller 2, I could put them in my digital multimeter and tell you what they are, but I won't. I do know that they're all 4 different sizes. And I have 2 smaller inductors that are removed out of switch mode power supplies and things like that. So I've got this really small one, a slightly larger one, and as I said, this really large inductor. So given this and a simple breadboard, I'm going to use a lead that I just made up to come out from the Agilent waveform generator. It's going to provide me the various square waves that I'm going to use to verify the inductor and the capacitor values through timing, using the oscilloscope to do the measuring. So right now I don't have anything hooked up, so I'm starting from scratch so that you can see everything we're doing. The general principle, if I just clear this away for a second, is that if you put a resistor, can we see this? Yes, we can. Good. If we put a resistor and then a capacitor, and then we measure the oscilloscope here, and we put in a step on the input of the resistor, R, and we have C. If we know what R is, so let's just say 100K, and we know what C is, and we don't know what C is, but what will happen is, over time, if we measure this point here, we will get a stepped output, a exponential output. It'll rise and slowly taper off. And with a capacitor, the capacitance is equal to the time you measure over the resistance. All right. Now, normally it's T equals RC, but we've just rearranged it because we don't know what C is, and we're going to calculate that one. T for capacitors, when you're doing this kind of timing, is roughly 63% of the value of the supply voltage. So the minute I put this pulse up to, say, let's just say a 1-volt pulse or something like that, the capacitor will immediately start charging with the RC constant. When it reaches 63% of the full voltage, or in this case 630 millivolts, because I'm going to give it a 1-volt input, then that time from when we applied the edge to when we reach there, put into this formula, will give us a time constant so we can figure out the capacitance. Now, before we get started, what I want to do is measure the resistors so that we know exactly what value they are. We know what the nominal value is, but in order to get the maths a little more accurate, we're just going to measure them more precisely. So the 100K is actually 100.7, well, let's just say 0.8 K. The 10K, I'm not bothering to null out the meter because there's relative to the resistor values it's insignificant. So we've got 9.96 for the 10K. And for the 1K, this just allows us to get some more accurate calculations once we start doing the math to figure out the resistor values, the capacitor values. So for the 1K, it's 1.001. So these are actually pretty good. Okay, so what do we have here? We have the output from the pulse generator, the Agilent 33622A. I've set the frequency to 100 Hertz, square wave, with a 1 volt peak signal offset with at 0 volts. The positive output of that goes to currently the 1 kilo ohm resistor. I've got the 1K, the 10K, and the 100K, the 1K, 10K, and 1K all plugged into one bus line of my breadboard, and I've got our first random capacitor plugged in, ready to do the measurements. Now I just want to demonstrate something to you right off the bat here, because I haven't plugged in the negative to this capacitor yet. So all I have currently is the 100 kilo ohm resistor in this circuit. I want to demonstrate to you one of the issues that you need to be aware of when you're measuring circuits with things like oscilloscopes and multimeters and things like that. So if I just get the signal on the display here right now, as you can see, I've got the 1 volt signal. I'm going through 100K, so I've got times 10 probes, so it's basically 10 mega ohms on the probe. So it's going to have almost insignificant issues with that. Pretty sure that's what I have it set to. Let me just verify. Yeah, 10 times. So that's 10 mega ohm input impedance there, and I have 100 kilo ohm here. I've set my amplitude to 1 volt peak to peak, and I just have the grounds across but not the negative of the capacitor. So on the input to the oscilloscope, I've got it set to times 1. That's why I was getting a funny value. Let's go back to times 10. I've got it set to times 10, so it's 1 volt, and remember I said it's 1 volt peak to peak, so what we've got here is negative 1 volt and then plus, so it's basically 2 volts. Agilent pulse generator set to a 50 ohm output, and of course I have a high impedance load on here, so the Agilent's only showing 1 volt peak to peak. If I change the output to show I've got a high impedance load, then we'll get the correct reading, which is 2 volts. So we have 2 volts peak to peak. The oscilloscope is showing 2 volt peak to peak. We only have the scope probe connected right now and the square wave, and you notice it's a little bit off, but if I expand this out and actually have a look at the edge of this square wave, you'll notice that it is not square. Okay, if I just zoom in a little bit on that so you can see a bit better. Alright, it is not a square wave. It is primarily, but there is a rise time to it. So if I increase this, one of the things to remember for when you're doing this kind of measurement, 63%, if I increase the amplitude of this signal to 8 divisions and I simply measure across the first 5 divisions, that gives 62.5%, which is close enough accuracy, and it makes the measuring a lot simpler. So if I just simply reduce my scale so that it sits on the 0, which it is now, and up to the maximum voltage here, sorry, maximum scale, I'll just adjust this so it's sitting on 0, which it is now, and if I just increase the time scale so that I can see enough of this waveform, what I will do now is I'll use the cursors to actually measure. I'm going to put channel 2 on and put it on the 5th division. So 1, 2, 3, 4, 5. I'll bring that down to the 5th division. So when it crosses this line, that is where it is going to be at the 66% point. So we'll take our first cursor and we will move it to the beginning of the pulse. This is where the square wave starts to rise. And we'll take the second cursor and we'll move it to where it hits 66%, which is right here. Sorry, 63%. Okay, so it's right there. And that's about 1.56 microseconds. Alright, so if we write this down for now, we'll do the calculations later. It's important to note why I'm doing this is that it's, what did I say, 1.56 microseconds. Right. 1.56 microseconds is the value that I'm getting with a 100K, 100.8K All right. So the output of the Agilent waveform generator is a very, very fast edge. It is not as slow as 2 or 3 microseconds. It's in the range of picoseconds or nanoseconds. Sorry, not picoseconds. It's in the range of nanoseconds. So what is causing this? Well, the oscilloscope probe is basically what's causing this. It has a 13 picofarad load on the actual input of the oscilloscope, and then you have an additional 2 or 3 maybe picofarads on the actual probe tip as well. So these effectively end up being in parallel, giving you about 15 or 16 picofarads loading on your signal. So even though I don't have a capacitor in here at all right now, my square wave is already being put through an RC network and causing this curve where we can now measure. And what we'll do in a moment when we start doing the calculations is we'll actually verify the input capacitance of the oscilloscope with these probes that I've got. Anyway, so the way to now bring in the capacitor that we want to test is I'll simply connect it to the other side of the capacitor now, and you notice that this has completely changed now, the waveform, because it's way, way slower now. So if I reduce this down, we'll see that we basically have the same kind of edge. Now right now the pulse width, the frequency is too high for this capacitor, so I want to make sure that it is completely leveled off before it goes to the next cycle. So I'm going to change the frequency and bring it down to maybe half that, so maybe 50 Hertz or something. Alright, let's see if that's enough. Yeah, so we're just getting flat tops now and a flat bottom, so that's enough to be able to do our measurements. Now let's just adjust this back to the point where it's sitting on the top and bottom rails, which gives us the full 8 divisions, which is right about there. And I'll increase the bandwidth, the time base again, so we're running at 250 microseconds per division. And if I now just adjust my markers so that I can get a period out of this. So we have cursor A sitting right in the start of the pulse, and I'll move cursor B now to sit at the 66% mark. And what we have here is roughly 1.17 milliseconds. Now this is with a 100K resistor in here, so I put my pen down somewhere. I bet you can see it on the video and you're screaming out at me saying, there it is. Yeah, see, told you. Alright, so C1 with 100.8K is giving us a time of 1.17 milliseconds. If I reduce that to a 10K resistor, which will probably give us a more faster period, alright, you can see that's a lot faster now. I can probably take this frequency back up to 100K, and it's going to make no difference here. But if I now bring this out, so we'll just do it with 2 different speeds so that you can actually see that it's not necessarily a function of the frequency. So if you look at that, now I haven't touched cursor A or B of the oscilloscope at all. I've increased the frequency going in just for the sake of the time base, but all I've done is change it from a 100K to a 10K resistor. I've increased the time base to 25 microseconds now, and if you look, the 66, without moving the cursors, the 66% is still crossing where the blue line is, exactly where it was before. The difference is now it's 117 microseconds. Okay, so I'm going to write that down for the 10K, which is 9.96K, and 117 microseconds, so 117 microseconds. If you noticed, before with 100K I got 1.17. Now that I've got a different frequency but also a different resistor, I'm getting the same actual numbers, just with a different period because of the different values. So that's probably enough for that capacitor. So I'm going to rip this one out while I'll just do it live while we're videoing, and I will connect a new one to make sure you can. I just realized that you're not actually watching the screen, what I'm doing down here, so apologize for that. I'll bring this into circuit now, so, sorry, into view, so you can see everything going on. Alright, so I'm just pulling out this capacitor. This is the one that I've just finished playing with, okay? So, I don't know if you can see there, but you better see the colors. It's brown, black, orange, black, red. Okay, so that's C1. So let's take C2 now, which is physically smaller, and we'll put this into the circuit, and we'll see what values we get with this. So I'll put my measurement probe back on the end of the capacitor, take my grounds and put them both on the other leg of the capacitor. Now we're still running with a 10 kilo series resistor, no, it's a completely different capacitor. Now you can see this capacitor is a lot higher value because right off the bat the oscilloscope trace is much shallower. So if I reduce the time base now, you can see it's again not getting to the flat tops. So what I'm going to do is I'm going to reduce the frequency a little bit, right? So that's 90, 80, 70, so about 70 hertz, 60 hertz. Let's just go a bit wider. So that's good. So this is a higher value, and let's just now bring this out so that we can get a decent amount of the waveform there. You can see this is now not making the cursor, so we'll have to readjust this so that we do. I'll just move that onto the cursor A so we've got plenty of width available, and I will adjust cursor B so that it hits the 66% mark. So now we're looking at about 980 microseconds for this one. So this is C2 and we've got 980 microseconds, and we have the 9.96 kilo resistor. Right? Now I'm not going to bother doing the same thing as we did with this one. I'm just going to do the one value. You'll see when we do the math on the first one they're going to be the same. And I'm going to pull this capacitor out now. That one here. Now the next one we're going to use is actually an electrolytic. But because we're using such a low voltage, it really isn't going to affect the electrolytic at all. So we should be able to just put this in, and because it's basically floating here as well, it's not really going to matter anything. I wouldn't do this with any high voltages on a capacitor like this, but this is just fine for what we're doing here. So I'm reconnecting that, putting the probe back on here. Now this one we're probably going to find, because it's electrolytic, it's going to be a much higher value. It's going to be giving us a much slower signal. As you can see here, it's not even registering. So what I'm going to do is I'm going to switch to the 1K resistor here, just to increase the resolution, or at least so I don't have to reduce the time base to some crazy value. So the frequency is still a bit too much, so I'm going to reduce this down to maybe 10 hertz. Yeah, that's sufficient there. So now we've got a 10 hertz square wave. We've still got this characteristic curve of an RC network, so I'm going to increase my time base out again so that I can do some measuring here. Adjust this onto the first cursor, just being lazy rather than move both cursors, and move this second one to the intersection of the 63% mark, which now is reading 5.5 milliseconds. Alright, so C3 is 5.5 milliseconds, and we have the 1.00, so a 1K resistor for that one currently set. So that's pretty good. Now the last one, C4 here, let me just get that inductor out of the way. We'll just quickly place this one on. I don't have a less than 1K resistor quite to hand right now, but that's fine. We'll be able to just slow the time base down to get a reading off of this. So this one's a 10 volt capacitor, so we're still going to be fine. Alright, going to connect the scope probe back in, connect the ground to the negative, and the signal negative. Alright, so this one's going to be a lot slower, so I'm going to reduce the time base down. And as you can see, it's not getting enough time, so we're at 10 hertz, so I'm going to reduce it right down to probably about 1 hertz. to give it a chance to charge. And that's still not quite enough. Am I connected correctly here? Yep, so I'm going to reduce that down even further to maybe 1/10 of a hertz, so 10-second cycle. So what I'll do here is I'll stop it as it's already gone through. So as you can see here, I've just stopped it, but it's actually already gone enough of the trace so that we can do some measuring. And I should be able to just slide this across to line it up with the cursor A. Okay, and now I'll adjust cursor B to hit the intersection. Alright, so 1.1, yeah, 1.11 second on this last C4. So it's 1.11 seconds. And that again was a 1K resistor. Alright. So, how do we know what value these are? Well, we'll do the math in a moment. We're just going to now switch to doing the inductor. So without even knowing the capacitor value, I'm going to do some inductor measurements. And what we'll see is that by having a known capacitor, which we'll actually calculate in a moment, and we'll use an Excel spreadsheet on a screen capture so you can see it, we can then use that with by measuring the period of oscillation to figure out what the inductor values are. So now let's just reconfigure this so that we can check inductor values.